Okay, in the last example, we saw that these three vectors form a basis for all of R3. And so, for example, if I did a linear combination of these, let's just pick something. Let's say one of these minus two of these and plus one of these. I'm just making up some numbers here. But let's see what that ends up equaling. So if I look at the x component here, 1 minus 4 is negative 3 plus 3 is 0. 2 minus 18 is negative 16 plus 3 is negative 13. And 1 minus 0 is 1. Plus 4 is 5. So that's how you could represent the vector 0, negative 13, 5 as a linear combination of the three vectors that we saw was a basis for all of R3. And so what we want to talk about now is the coordinate vector. So what the coordinate vector is, remember that coordinates are the coefficients for the basis vectors that we're using. So the coordinate vector is the vector that is made up of those coordinates. So for example, for the vector 0, negative 13, 5, the coordinate vector relative to this basis, and by the way, this basis, when we say it, we're talking about the vectors in that specific order. This one first, this one second, this one third. The coordinate vector for that is 1, negative 2, 1. And the way that we write that, so I have 0, negative 13, 5. We typically write a parentheses around that, and we'll write a subscript b if b is this particular basis. Maybe I should write that here. So the coordinate vector relative to that basis is the vector 1, negative 2, 1. And you could write it like that, or you could write it like this. Again, it doesn't really matter how you want to write that. Now, if I used a different basis, for example, if I use the standard basis, which is, again, 1, 0, 0, 0, 1, 0, 0, 0, 1, obviously the vector and the coordinate vector are the same because it would take none of these. This is the only one that would contribute here. Here would be the only one that would contribute to the second component, and this one would be the only thing that contributes to the third component. So, relative to the standard basis, the vector is going to be the exact same. But if it's not the standard basis, then it will look a little bit different, as this one does here. And so what we want to do is we want to see what the coordinate vector of each one of those would be. So in the example from the notes, for A part, let's take the vector ABC in R3, and let's find the coordinate vector relative to the standard basis. Well, I just mentioned that, right? For example, ABC is A times 1, 0, 0 plus B times 0, 1, 0 plus C times 0, 0, 1. And so ABC, that vector, its coordinate vector, so let's say relative to S, is actually still the same thing. It's still ABC. And if you wanted to write it like this, you could. Right? So using the standard basis is actually a kind of a natural thing to use. It's when you use something that's different, where you can have something like this one up here, where the numbers are not necessarily what you would expect, I guess. So for the second example, we had a polynomial, C0, C1x, C2x squared, all the way up to Cn xn, and that is in Pn. Remember, that's the set of polynomials degree n or less. And let's use the standard basis one more time. Well, remember that the standard basis for Pn is the basis 1x, x squared, all the way up to x to the n. So you can kind of see that this particular polynomial corresponds to the vector C0, C1, C2 down to Cn. Right? That's what this written as a vector is. But of course, that written as a vector relative to the standard basis is going to be the exact same thing, right? There's no way for me to change, for example, this to something different and get that same constant. Because x squared up to x to the n, they don't give you a constant, right? They give you x or x squared or all the way up to x to the n, right? So let's take a look at the third one, because this one's a little bit more, it's a little bit different, I guess we should say. So I want to write, actually it's not different, sorry, I was thinking of a different problem. But A, B, C, D, if I want to write that as a linear combination of the standard basis in M22, and by the way, M22, this is the standard basis. So notice the only one of these four matrices that contributes to the first row, first column entry is this one. So it's going to have to be multiplied by A. And notice these are all zeros, so it contributes nothing here. So similarly, you would make that B, this C, this D, and you would add those together. And that one's pretty straightforward to make it add up to this. And so therefore, you could say that the, if we call this B, I think that's what I called it in the problem, then B relative to, again, let's just say the standard basis S, I'm going to write that, I'll write it this way. That is A, B, C, D. Notice that I'm not writing this as a matrix. The vector here, the coordinate vector, is always written as a vector. Whether you write it as a column vector or a row vector is up to you, but it's always going to be like this. And because it's a vector, the order is important. So when you talk about a basis, it's not enough to just say it consists of these vectors. You have to say it consists of these vectors in this order. And so therefore, that's how you would have to consider this when you're coming up with a coordinate vector. Hopefully that makes sense. If you have any questions, let me know.